Hello everyone. So we are continuing our discussion on surface plasma and polariton. So last time we discussed about the TM mode where we found the dispersion relation for the situation. Now if we just take up the TE mode, the other set of equations that we had found out, then what we have is for Z greater than 0, which is basically your dielectric, there you have for TE mode, practically the three equations are the ones that relate EY, HX and HZ. So it's the transverse electric field. It will not have any component along the Z direction. The form of EY, as we can write down, is A2 exponential IKXX and exponential minus K2Z. This is for the Z greater than 0. Yeah, this is for the dielectric part. Okay, and so once we find out use the other equations from the Maxwell's relations that we have, we will also get Hz is equal to A2kx by omega mu naught exponential ikxx exponential minus k2z. The k2z, remember, it is the evanescent field that we had, and the hx will turn out to be the same way as we had solved for the TM mode. It should come out to be something like this: k2a2 by mu naught omega, the same three factors, I, kxx, k2z. Okay, and similarly, if you calculate for the z equals less than 0, that is in the metallic region, then, or the conducting region, you have EY to be, now instead of A2 it will be all A1 and K1. So exponential I kxx exponential k1z. Please note, in all these relations, because z is negative here and it has to be an exponentially decaying function, so we have exponential e k1z, where z is a negative number, so it will be an exponential decay. So in all these, k2 and k1 are all positive numbers. These are the decay constants that we had: a1 kx omega mu naught exponential I kxx k1z. These factors are same, and finally we have hx is equal to I a1 k1 by omega mu naught exponential. So this is what we have as the 6 relations. So these 3 for the upper region, which is the dielectric, and these 3 for the conducting region. Now, of course, the next step would be to implement the boundary conditions. So boundary conditions, what we do is it's actually conditions that the Ex component, that is the parallel component of electric field, is continuous across the interface. So if you plug it in, so you at z equal to 0, so what we have is this relation, and this relation. If you say at z equal to 0, these two terms cancel, and what you land up with is, from the continuity of electric field, continuity of T of EY, continuity of EY, what we get is A1 is equal to A2. This is what we get, and the other term what we say is that Hx is also continuous across the boundary, okay, because there is no free current in the interface, so the Hx is also continuous. So continuity of Hx at z equal to 0 across the boundary. If you plug things in, what you get is minus k2a2 is equal to k1a1. Okay, if that is the case, and substituting a1 is equal to a2, what we have is a1 k1 plus k2 is equal to 0. Now since k1 and k2 both are greater than 0, they are all positive numbers because they define the decaying of the evanescent fields. That's why this term in the bracket can never go to 0. So all we have to do is, so to get this equation running, to have the boundary condition, it will imply that a1, which is equal to a2, should be 0. That is, the amplitude of the fields are 0, which means that SPP, surface plasmon polaritons, do not exist for TE mode. Okay, so for TE mode of light, for lights in the TE polarization, you will have no surface plasmon polariton. So it has to have TM component to generate these. Okay, so that is where we end today's lecture. Thank you.